Good afternoon, ladies and gentlemen. Welcome to another exciting episode of Dave Does Math from Home. On today's episode of Dave Does Math from Home, we are talking about section 4.4. This is where we're going to start graphing functions. To be completely honest, this section is it's like 90% of this section is exactly what we did in the last section. The only difference here is we're gonna do everything we did in the last section, exactly the same as we did it in the last section. There's no changes there. We're just gonna go one step further after we've done all those things and sketch a graph of these functions now that we know where they have maxima and minima. In a lot of ways, this section is gonna feel like in pre-calculus we had a section on graphing polynomials. We graphed these polynomials by finding the local behavior and the end behavior. And the local behavior was intercepts, x-intercepts and y-intercepts. And we got the x-intercepts by factoring the polynomial, setting equal to 0 and factoring it. This section is going to be almost exactly the same. We're going to be graphing these polynomials. We're not going to use x-intercepts. A lot of the polynomials we're graphing here, in fact most of them, are going to have irrational x-intercepts. These are not things you can find by factoring. Sometimes if they're quadratic, they're things you can find using the quadratic equation. Most of the time they're going to be things that are just not easy to find analytically. So we're not going to be doing any x-intercepts at all on these graphs. Instead, we're going to be using local extrema as sort of the anchor points that we're going to fix our graph to. So we're not concerned about where it crosses the axis, we're concerned about where it peaks and where it has minimums. That's what we're going to use to graph it. Other than that, this works almost exactly the same as section 4.3, like I said. So we're just going to start doing examples and then see what that feels like. I'm going to start with a fairly straightforward one. We'll start with f of x equals x to the fourth minus 4x cubed. This is a fourth degree polynomial. I want critical points, because those are going to turn into my maxes and mins. So we'll say f prime of x equals 4x cubed minus 12x squared. I'll set this equal to 0. We can factor some stuff out. I'll pull out the 4x squareds and be left with an x minus 3 equals 0. Which means I have critical points at x equals 0 and x equals 3. Critical points. So, I need to use either the first or the second derivative test to determine whether these are maxes or mins. For this problem, I'll use the first derivative test. We got 0, we got 3, these are x values. Above them, I will put derivative values. Derivatives here are 0, 0. When x is negative, big negative numbers, we're going to have something like, we'll say like negative 10. This will be negative 40,000. And this is irrelevant at that point. So this will be very negative. This function is decreasing to the left of 0. Here, we can probably plug in something like 1. That would be 4 minus 12. That's negative 8. So it's negative again. It's still decreasing here, though it pauses in the middle of its decreasing. It pauses to go flat for a second. And here, numbers bigger than 3, we'll use 10 again. This will be positive 4,000 minus. Is this right? Yeah, positive 4,000 minus 1.2 thousand. Still positive, yeah. Okay. So it's decreasing, goes flat, stays decreasing, and then increases. So this is it's not anything. This is a local min. So, the first big departure or I should say, if we were doing this as a 4.3 problem, we would be finished. This would be the end of the 4.3 problem, because we've identified all the local extrema. They're there. Because this is a 4.4 question, and we're going to graph it instead of ending here, we need to do 2 quick extra steps. The first extra step is we're going to find y values. I know that x equals 0 and x equals 3 are the critical points. Those are the x values at the critical points. But I need actual points if I'm going to graph this. So I'm going to find y values. I want f of 0. I think that's pretty clearly just going to be 0. And I want f of 3. That's going to be 81 minus 108. Looks like negative 27. Okay. These are the 2 points I have, and believe it or not, these are the only 2 points I need. Although I should also consider the end behavior. That hasn't changed since pre-calculus. We're still doing end behavior. We have a positive even degree polynomial, so the end behavior here is going to be a field goal. So we are ready to graph this thing. I have a point here at 0, 0. I have a point here at 1, 2, 3, negative 27. And I know how this graph behaves in between these points. I know to the left of this it is decreasing, which means as it moves, it is decreasing from left to right, which means that if we go from right to left, it should be rising towards its end behavior. I know that here it gets flat for a second, but then it keeps decreasing to this. This is its minimum. And past there it will increase. And that's it. That's the whole graph. We're finished. Let's do another one. Let's do f of x equals negative 1/4 x to the 4th plus 2x cubed minus 4x squared. Plus 3. Once again, the goal here is to create a graph of this by finding critical points and for finding all the local extrema. So, first step is I need a derivative. It's going to be negative x cubed plus 6x squared minus 8x. So I'm going to set that equal to 0. I'm going to factor out a negative x. I'll be left with x squared plus, minus 6x plus 8 equals 0. I'm going to factor that. That'll give me an x minus 2 and an x minus 4. That all equals 0. So I have x equals 0 and 2 and 4 are my critical points. For diversity, I'll use the second derivative test. My cat is making some very strange noises. I'm going to use the second derivative test to determine which of these is max and min. F double prime of x is, this is the first derivative, then the second derivative should be negative 3x squared plus 12x minus 8. So f double prime of 0 should be negative 8. That's not how you draw an 8. Negative 8. So if this is negative, that means it's concave down, which means that this is a max. We can do f double prime of 2, which is going to be negative 12 plus 24. So positive 12 minus 8 is 4. So if this is positive, it's concave up, which means we have a min. And f double prime of 4 is going to be 16, negative 48 plus 48 minus 8 is negative 8 again. I keep drawing that sideways for some reason. I'm not actually thinking about infinities in any capacity here. So this is a max, just like the last one was. This is useful information, but it is not enough information. This is where the problem would end if this was a 4.3 problem, but I want more this time. I want to know the y values here so that I have actual points so I can use them as a graph. So let's find some y values. F of 0 is 3. F of 2 is a mess. 2 to the 4th is 16, so this will be negative 4 plus 16 is 12 minus 16 is back to negative 4 plus 3 is negative 1. And f of 4 is, this will be negative 64 plus 128 is positive 64 minus 64 is 0 is another 3. That's not so bad. I'll take it. So I have these 3 points. I know that there are a maximum, a minimum, and a maximum locally. I need some end behavior. This one is also 4th degree, so it's going to be doing the same thing on either side, either both up or both down. And it's negative, so hammer time, both going down. So let's draw a graph. I should give myself more room on the right, since that's where all of my points are. Okay. 0, I'm up here at 3. At 1, 2, 3, 4, 2. I'm at negative 1. And at 4, I'm back up to negative 3. And on either side of this, I'm falling. Here's my graph. Got maximums at 0, 3, and 4, 3. And a minimum at 2, negative 1. That's it. That's the entire section. We're taking everything we did before and we're doing that the same. That hasn't changed at all. We are adding y values, an end behavior, and then we're sketching a graph. That's the whole thing. If you can do 4.3 and you understand end behavior and how to draw a graph, then you can do 4.4. It's not so bad. Stay tuned for more videos. The next section is a good time. We're going to be doing optimization problems like this, finding maximums and minimums, except we're going to do it to story problems.